Hello guys, hope you are doing well. In this session I will be talking about the first section of chapter 6, which is about the chemical equilibrium. Guys, the chapter 6 is all about 4 sections. The sections are in general talks about the equilibrium and the state of equilibrium in chemistry. Section 1 is all about the nature of chemical equilibrium. Section 2 will be talking about the shift in equilibrium. Whenever there will be stress on a reaction at equilibrium, there will be shifting to the right, to the left. And then equilibria of acids, bases, and salts. And then the last section is all about the solubility product, which is KSP. Guys, let us talk about the first section and the nature of the chemical equilibrium. For almost all the reactions in chemistry, theoretically, we have a reversible process. We mean whenever a reactant undergoes through a process to form a product, theoretically, most of the reactions are reversible. We mean the product, they have tendency to back to the reactant. And for those reactions which are reversible, the product, they have tendency to back to the reactant, there is a possibility for reaching equilibrium state. What do we mean by the equilibrium state, guys? Equilibrium state simply how many amount of the reactant consumed to form product at the same time, simultaneously, the same amount of product backs to the reactant. So there will be both directions with the same rate. Both directions with the same rate. That's simply the equilibrium. In a system that are in equilibrium, guys, opposing processes occur at the same time and at the same rate. So, simultaneously with the same rate, those processes, the forward and reverse processes, are occurring. An example for equilibrium, guys. When an excess sugar is placed in water, some sugar molecules go into solution and some of them remain undissolved. Guys, whenever we add some sugar into the solvent, there will be dissolution or dissolving process. Dissolution process is dissolving salt in the water, but the opposite of that process is the crystallization. So when the equilibrium of this process can be reached, when the rate of formation of or the rate of the crystallization equals to the rate of the dissolution. How many molecules of the salt dissolves? The same amount, the same molecules, the same specific amount of the molecule must dissolve or must crystallize. So at equilibrium, molecules of sugar are crystallizing at the same rate that molecules from the crystal are dissolved. 2 molarity of the sugar dissolves, the same 2 molarity crystallizes. There will not be any change in the concentration of reactant and product during the equilibrium. Solution equilibrium is a physical state in which the opposing processes of dissolution and crystallization of a solute occur at equal rate. Here we have got the dissolution process and the crystallization. If both rates are equal, that means we have a solution equilibrium. More examples, guys. For example, the rate of the evaporation of a liquid in a closed vessel can eventually be equal by the rate of the condensation. So we have evaporation and condensation. So when these two processes, the rate of evaporating the amount of the liquid to vapor and the rate of the condensing the vapor to the liquid becomes equal, that position we call the equilibrium of the reaction. The resulting equilibrium vapor pressure is a characteristic of the liquid at the prevailing temperature, guys. Example for physical equilibrium. Some of the physical equilibrium in our daily life we have dissolving a sugar and crystallization as well of it, to both processes at the same time. Evaporation of liquid and condensation of the gas to the liquid. Dissolution of gas effervescence. This is whenever we add gases to the aqueous solution, we dissolve the gas, and then whenever the gas escapes from the solution, we call as the effervescence. And we have got some of the examples physically here, guys, showing when the NaCl dissolves and then the Cl with the Na crystallize to form NaCl. When sugar dissolves, will form sugar, and then the process of the crystallization and the dissolution equals. When H2O liquid evaporates, and then when it is condenses. We have reversible reactions, guys. Theoretically, as I told you guys, every reaction can proceed in two directions, forward and reverse. So in chemistry, theoretically, it's not practical because some of the combustion reactions are not reversible. Usually the combustion reactions are not reversible. Even some of them are reversible. They are reversible with having specific conditions of temperature, pressure, and the system must be in a specific situation. Guys, a reversible reaction represents by a double arrow. What do we mean by a reversible reaction? Means when the rate or for example, the R reactant goes to product, the reactant form the product, this is the forward. If the product has tendency to back to form the reactant, that will be a reversible reaction. A chemical reaction in which one or more reactants converted completely to product is called what? Irreversible reaction, and represents by a single arrow. With a reversible reaction, we have irreversible reactions as well. Irreversible means the reactant converted to the product, but the product has no tendency to back to form the reactant. For example, here we have an example for a reversible reaction. Mercury 2 oxide decomposed to form mercury and oxygen gas. In another example, in another process, the mercury with the oxygen combines to form or synthesize mercury 2 oxide. This reaction is a reversible reaction. We have provided some example for the physical processes or physical equilibrium and physical reactions. This is an example of a chemical reaction, and in our book we mainly concentrate on the chemical equilibrium and chemical processes rather than the physicals, guys. As you can notice, guys, mercury 2 oxide heated, the form of this delta means heated, to decompose to form mercury and oxygen gases. And then mercury and oxygen to form mercury oxide. This is a process we call as the reaction as a reversible reaction. When the product they have tendency to back to form the reactant, that's a reversible reaction. Once the decomposition has begun, the mercury and oxygen released can combine to form mercury two oxide again. Thus, both reactions, the decomposition and the synthesis reaction, can proceed at the same time. They are processing at the same time. Under these conditions, the rate of the synthesis reaction will eventually equal that of the decomposition reaction. They will reach to a position which the rate of the synthesizing mercury two oxide and the rate of its decomposition reach to a position that both rates are equal at the same time. At this point, guys, a state of dynamic equilibrium has been reached. We will be talking about dynamic equilibrium. Dynamic means there is movement between in both directions, in the forward and the reverse. And it's at equilibrium because at the same time, the rate of the formation of the mercury two oxide equals to the rate of its decomposition. So the reversible chemical reaction, as I told you, we mainly concentrate on the chemical equilibrium, is in chemical equilibrium when the rate of its forward reaction equals to the rate of its reverse reaction and the concentration of its product and reactants remain unchanged. So we have to know that the concentration remain unchanged, not equal. It's not, we'll be talking about three cases of equilibrium. It's not necessary for equilibrium to be reached with equal masses, equal concentrations of reactant and product. But it's necessary when the equilibrium reaches, the sign of the equilibrium is that the reactant and the product at equilibrium position remain unchanged, the amounts of reactant and product. This can be represented as a combined reaction, both processes. AgO form Ag and oxygen, and AgO and oxygen backs to form AgO bio, represent the double arrow, and this represents what? A reversible process or a reversible reaction. And the procedure is represents in the figure 1 when the mercury two oxide heated, there will be oxygen gas and liquid mercury, and then at the closed container, these two they have tendency to back to form mercury two oxide. Let us talk about the equilibrium at dynamic state. What do we mean by equilibrium at dynamic state? Guys, equilibrium, we may guess that at equilibrium there will not be the formation of the product and the reactants. The reaction stop. So that's not a correct explanation or not a correct thought about the equilibrium. The equilibrium is that when both directions are in progress, the forward and the reverse are in progress without changing the concentration of the reactant and product with the same rates. At equilibrium, we can say that the net movement or the net changes of the concentration between reactant to product is zero, because any amount of the reactant consumed to form the product, at the same time, the same amount backs to reactant, so there is no change in the concentration of reactants and product, the net zero. Guys, many chemical reactions are reversible under ordinary conditions of temperature, concentration, and pressure. So, in order to reach to equilibrium, all of the reactions they do not reach to equilibrium within the same temperature or same concentration of reactant and product or same pressure as well. Individual reactions, they reach to equilibrium with different conditions of temperature, pressure, and concentration of reactant and product. This tells us that to reach to equilibrium, every reaction has its own properties or its own conditions of the system. So the equilibrium can be reached with different temperature, concentration, and pressures for different reactions. We will be talking about the shifting equilibrium in section 2, which by changing these quantities, the concentration, pressure, volume, and temperature of the system, that disturb equilibrium and shifts the equilibrium to the product or to the reactant. So changing these conditions change the equilibrium position as well. Note that at equilibrium, reaction proceeds in a closed container, so substances cannot escape or remove it from the reaction system. For an equilibrium to reach to equilibrium, the reactions must be reversible. That's why we talked about reversible reactions. If a reaction is not reversible, it cannot reach to equilibrium position. Why? Because there will not be the reverse direction. And equilibrium is that when the forward and reverse direction, they are both occurring at the same rate, at the same time with the same rate. And with this condition that the reaction should be reversible, there is another condition that the system should be closed, because sometimes you may have gases and some other products may escape from the system, so we have to perform the reactions, the reversible reactions in a closed system in order to let the product to form the reactant and to be a reversible reaction. We have 3 cases of equilibrium, guys. 3 cases of equilibrium. The 3 cases, why? Because you may guess that equilibrium is a state in which the concentration of reactant and product are equal. That's not the correct thought about the equilibrium, as I told you previously. Here we will be representing that equilibrium in the first case, that the product is higher than the reactant concentration under equilibrium reached. Second, equilibrium reached, but the reactant concentration is higher than product. Third, the equilibrium reached and both concentrations are equal. So among those 3 possibilities, only one possibility is for the equalizing the concentrations and then becomes equilibrium. The first one, guys, the forward reaction is predominant, that essentially all reactants will react to form products. We have some reactions, guys, in order to reach to equilibrium, most of the reactant must be consumed to form the product. Should consume the large amount of reactant to form product in order to reach to equilibrium. So the arrow represents by a longer arrow toward the forward and a shorter one toward the reverse. Means what? Means this reaction, the product of forward reaction, our favorite, means K higher than 1. We'll be talking about the equilibrium constant K. And in this case, guys, the amount of product is higher than the amount of reactant. So this arrow represents what? Whenever the longer arrow is toward which side, that means the formation of that side is more. And the concentration of that side is more. The shorter arrow is toward the right, so the formation of the right is much lower than the formation of the left. The formation of the left is much lower than the formation of the right, if we count like that. So this arrow represents what? The equilibrium reached with the higher concentration of product than reactant. The higher concentration of product than reactant, but the rate of forward is equal to the rate of reverse. Means what? Means it's in equilibrium. And to this we call the equilibrium lies to the right. Lies to the right means what? Means equilibrium reached with the higher concentration of the product. This we have explained the meaning of the arrow, that inequality of arrow, longer arrow, to imply that product side favored in this reaction. The second case of the equilibrium is the opposite of the first, guys. The equilibrium reached with the high amount of reactant than the product. A high amount of reactant than the product. As an example here, guys, we have carbonic acid reacts with H2O to form hydronium and bicarbonate or hydrogen carbonate. Guys, the representation of this arrow means what? Means the longer arrow is toward the left, and then means the reactant side has a higher concentration than the product, and the reaction reaches to equilibrium. So for this reaction lies, or the equilibrium lies to the left. Why? Because the amount of the product is lower than the amount of the reactant. This case, the reactant has a higher concentration than the product, and the reaction reaches to equilibrium. It's those reactions with converting a low amount of reactant to product reaches to equilibrium, and in a short period of time. But still, guys, this is at equilibrium, which the rate of the forward equals to the rate of the reverse, and K is smaller than 1. We'll be talking about that later. We'll be talking about equilibrium constant, K. The third case, guys, the arrow represents by equal length. Both arrows, they are equal in length. So in this case, we mean equilibrium reached with the equal concentration of reactant almost with the product. So neither reaction, is favored, and considerable concentration of both reactants and products are present at equilibrium. K is equal to 1, means the concentration of reactant almost equals to the product. And in this case, the concentration are equal, but still the rate of the reverse equals to the rate of the forward, means it's in equilibrium. The shifting is neither toward the left nor toward the right. In all of the above cases, guys, the reactions are in chemical equilibrium, means equilibrium can be reached when K is equal to 1, K lower than 1, K higher than 1. So these three cases to represent that equilibrium can be reached with different values of K, equilibrium constants. We'll be talking about that. When the product is higher than the reactant, means K higher than 1. The reactant higher than the product lower than 1. The reactant and the product are equal, equals 1. So let us talk about the equilibrium expression, how to represent the equilibrium, and how to understand the expression of the equilibrium. Guys, suppose that here we have a reversible reaction of AB proceed to form CD. AB proceed to form CD. This path is the path of converting A to B, AB to CD, and then the blue path is the conversion of the CD to AB. Guys, this reversible reaction, at the beginning of the reaction, when time is 0, so this represents this arrow what? Time, and here we have the rate of the reaction, rate. At the beginning, when time is 0, we do not have any products. So the reactant is at the top AB and the product CD are, here we have got A and B only. Here C plus D is 0. Okay, but as the reaction starts, at the beginning of the reaction, we do not have product. All the reactants, they are ready to be converted to react to the product, to form the products. As this reaction is reversible, AB at the beginning of the reaction convert to form CD, the forward reaction. And then the blue one, CD backs to form AB. Here in this case, guys, in this case, the forward reaction at the beginning is much more favorite than the reverse reaction. Why? Because at the beginning we have just the reactants, and the reactants, they have a tendency to form products. And as we do not have at the beginning the product is not available to back to the reactant. But as AB consumed to form CD, the concentration, the amount reduces. And here, as the AB converted to form CD, the amount of CD increases till it reaches to a point that backs to form the reactant. So it starts to back to form the reactant. This represents what? The conversion of CD to AB. Okay. They both reach to a position, guys. There will not be change in the rate of the reaction. The forward, which is converting AB to CD, is equal to what? The reverse, which is converting of CD to AB. So in this case, when the forward rate is equal to the reverse rate, on this line, guys, we call the reaction is at equilibrium. Is that the only graph to show the equilibrium? No, I will show you more graphs, guys. To reach to equilibrium, this is time, and this is R, rate of the reaction, 0, 50, 100, something. Guys, we have reactions that reach to equilibrium like this. So this is the forward and this is reverse. This is another graph that represents equilibrium. So equilibrium doesn't mean that always the concentration must be equal in order to be equilibrium, or to reach to a point, the same point, the rate be equal. So in this case, guys, how to know whether it's equilibrium or not? When we take the rates stay unchanged. So the concentration of the reactant and product stay unchanged. This is another graph which represents the equilibrium, and the forward and the reverse, they did not match. Another graph, guys, the form of the graph is that the equilibrium reached with what? With different graphical representations. This is another form of the graph which represents this forward and this one is reverse. So in this graph represents another graph for equilibrium. How do we know equilibrium reached? Because when we back to the R, and this is time, the R of both unchanged. So whenever the rate unchanged, we mean the equilibrium reached. That's the another representation, another graph for representing the equilibrium. So guys, we talked about how the equilibrium will be reached for reactions. At the beginning of the reaction, there is no product, only all the amounts are reactants, and so at the reactant begins, the reactant consumed to form product, and then the product starts to be formed and back to the reactant, reach to a position which the rate of reverse equals to the rate of the forward. We have got a note, guys, if reaction is not balanced at first, balance the equilibrium reaction. So to find the equilibrium constant we'll be talking, we have to balance the reactions always, guys. And how to write the equilibrium constant for any reaction, guys. Equilibrium constant, which is K, equals what? The concentration of product over the concentration of reactants, but raise it to their powers, and the powers are equal to the coefficient of reactants and products, equals to the coefficient of reactants and product. The constant K is independent of initial concentration. It's not depends on the initial concentration, and instead it depends on what? On the temperature of the system. So equilibrium constant, as other constants, change with what? With changing the temperature of the system, guys. Properties of equilibrium constant. What we have to know about the equilibrium constant, guys? The value of K must be obtained experimentally. So we obtain the value of K experimentally. What's the meaning if K is equal to 1? K equals 1. The reaction is at equilibrium. So guys, keep in mind that any value of K, 1, lower than 1, higher than 1, represents equilibrium position. Why? Because we measure the equilibrium constant at equilibrium position. There are roughly equal concentration of products and reactants. Almost the concentration of reactants and products are roughly equal to each other. Another value of K, which is less than 1, still at equilibrium, it means the reactant concentration is higher than the product. So less than 1 means the equilibrium reached with the higher concentration of reactant than the product, and then it can be represented by this arrow, which the reverse is favorite. We mean the term of favorite means the lies to the left. The K higher than 1 still is at equilibrium, guys, but a higher concentration of product than the reactant, and the equilibrium lies to the right. The equilibrium lies to the right. Another note about the equilibrium concentration, the equilibrium constant, only concentration of substances of aqueous and gases are included that can only change are included in K. So we will include those states that the concentration is changeable, which are the aqueous and gases. But solids, pure solids and liquids cannot change K because their concentration cannot change. So we do not include the solids and liquids in the equilibrium expression or in the equilibrium equation, guys. Equilibrium constant does not have exact unit, so we do not have a specific unit for the equilibrium constant. If a reaction is reversed, guys, the K reversed is equal to the K of the forward. I'll be showing you 3 cases how to find the K in different cases. One reversed, one multiplied, one divided. Later I will be showing. When we multiply the equation by a number, that number becomes the power of K. I will be showing later. K only changes by changing temperature. So you have to know that the only factor that changes K is what is temperature, guys. So what the equilibrium constant represents from the equation a mathematical product of concentration of the substances formed at equilibrium to the mathematical product of the concentration of the reactants. Each concentration is raised to a power equal to the coefficient of that substance in the balanced chemical equation. The equation for K is sometimes refers as the chemical equilibrium expression. So whenever requires to write the chemical equilibrium expression, that means you have to write the equation of K, which is the equilibrium concentration or the equilibrium constant. Here we have got a system of formation of HI from the hydrogen and iodine. The iodine and hydrogen here react with each other to form HI, and at the same time this is reversible reaction, as you can see, guys. HI has tendency hydrogen iodide to form iodine and hydrogen gas as well. How to write the equilibrium expression for this, and what should to be known about this reaction is, first you have to know that hydrogen is colorless, guys, as a colorless gas, but iodine is violet color, and HI is colorless. So at the beginning of the reaction, have a look on these three figures, guys. At the beginning of the reaction, the color of the system almost is violet. The color of the system, you can see that is violet. Why? Because at the beginning of the reaction, we have got H2 the reactant in the system. We do not have the HI. There is no product, as we have shown previously graphically. So as the H at the beginning of the reaction when time is 0, H2 and I2 exist in the system, and HI has 0 concentration. But at the reaction begins, so there will be a forward direction and also reverse direction. The H2 and I2 consume to form HI. So as you can see in the B, the color of the container becomes somehow approaching towards the colorless, or to be light violet. Why? Because here we have converted the H2 and I2 into HI, which is colorless. So consuming the violet to form colorless. And then finally it reaches to a color with a constant color, which is this case it reaches to equilibrium. It's neither colorless nor violet. Why? Because this reaction is reversible, and H2I2 they have tendency to form HI, and HI has tendency to back to form the reactant. So when equilibrium reached, none of the colors, the colorless and the violet, predominant on the system. Why? Because there will be existence of both in the system, and both partially they exist, and that's why it reaches to a constant intensity of color. As you can see here, the hydrogen iodide gas is produced from gaseous hydrogen and iodine. The violet color of iodine gas becomes fainter as the reaction consumes the iodine. So as the iodine consumes it, it becomes fainter, lighter violet. The violet does not disappear but reaches a constant intensity when the reaction reaches equilibrium at C, which is at equilibrium. It doesn't disappear, the violet, and then it's not colorless as well. So here we have represents the system, but how to write the equilibrium, chemical equilibrium expression? Of course, the product, both the system is a gaseous system, so a gaseous system means all the reactant and the products are gases. The HI must be in the numerator, and then the other is H2 and I2 in the denominator. To the power of 2, why? Because its coefficient is 2, and H2 and I2 to the power of 1 because their coefficients are 1. That's how we wrote the K expression for that reaction. This is the table which shows the equilibrium concentration of H2, I2 and HI for several experiments. Concentration of H2 and I2, concentration of HI, and then the values of K are here given and represents. Guys, let us solve the sample problem. Let us solve a sample problem. Here an equilibrium mixture of N2, O2 and NO gases at 1500 Kelvin is determined to consist of how many molarity of N2? 6.4 10 to the power minus 3, 1.7 10 to the power minus 3 oxygen, 1.1 10 to the power minus 5 NO. Guys, the equation, the first step is we have to write the equation. How to write the equation? The equation is reacting of nitrogen and oxygen to form nitrogen monoxide. So here we have represents the equation. And then second, balance the equation. Nitrogen, oxygen to nitrogen monoxide. That's a balanced equation. And then do we have the concentrations? Because K is equal to what? K is equal to the concentration of product to the power of the coefficient, the concentration of reactants to the power of their coefficients. But guys, be careful. If there will be liquids and solids, we do not include liquids and solids in the expression of K. And then what's the concentration of NO? It's 1.1 10 to the power minus 5 square. N2 and O2, 6.4, 1.7 10 to the power minus 3. So the final K, the value of the K is what? 1.1 10 to the power minus 5. It has no unit, as we said. So that's the K, which is too small, guys. This small K represents what? 1.1 10 to the power minus 5. It's smaller than 1. So if it's smaller than 1, that means which is consistent with more N2 and O2 being present at equilibrium than NO. In this reaction, if the equilibrium expression of the constant equilibrium is lower than 1, means the reaction reached to equilibrium with the higher concentration of reactant than the product. Higher concentration of reactant than the product, and lies to the left. Another example, the practice, here we have got the practice. Nitrogen, hydrogen to form ammonia. So the reaction must be written here and balance the reaction, and also the status are gaseous. The concentration of nitrogen is given, concentration of hydrogen, concentration of ammonia. Requires to find the what? K value. So the K value here is equal to ammonia square, nitrogen 1 to the power of 1, and hydrogen cube, which is the coefficient is 3. So just instead of the equation, replace them by the values, and then you will get a value of K. As you can see, this is still like the previous example is what is less than 1. So this represents the equilibrium position of reaction reached to equilibrium with the higher concentration of reactant and product, and it lies to the left. The value of K is small, means reactants are favored toward the left side, is much favored, much concentrations. We have got another practice, guys. AB2C goes to form B2 plus AC. All the states are gases, as you can see, and the equation is balanced. Reached equilibrium at 900 Kelvin in 5-liter vessel. So the volume is given, the volume of the container. The mole of the reactants and products are given. How to write the K expression? The K is equal to what? AC to the power of 1, B2 to the power of 1, AB2C to the power of 1 because their coefficients are all 1. That's the expression. But how to calculate the chemical equilibrium constant to this reaction? The values of concentration must be known, but we do not have concentrations. How to calculate them? Concentration, you know that is equal to mole per volume in liter. So how many liters is given? 5. So in order to find for AB2C, its concentration is equal to how many moles of AB2C is given? 0.084 divided by 5 liter. The same for B2 concentration is equal to 0.035 divided by 5 liters. Concentration of AC is equal to 0.059 divided by 5 liters. So this is how we can convert into the concentrations. And as the concentrations are known, guys, so you'll get the value of K, and this K is much smaller than 1. That's why the equilibrium reaches with the higher concentration of reactant than product. Another reaction, gaseous sulfurous dioxide and oxygen gas to produce gaseous sulfur trioxide. So the reaction is given by a statement. Here we have converted into a formula equation. Sulfur dioxide with the oxygen to form sulfur trioxide, and then balance the equation, gas, all our gases, 2 SO2, 1 oxygen, 2 SO3. And how to write the K? Of course, the product to the power of the coefficient, reactants to the power of the coefficients. It's given that the concentration of SO2 is given directly 1.5 mole per liter, concentration of oxygen 1.25 mole per liter, concentration of SO2 3.5. So just calculate by adding, putting the values in the equation, you'll get 4.4 the K. 4.4 is much higher than 1. That this represents what? Equilibrium reached with the higher concentration of product than reactant, and the product is much favored. Guys, the section review question 9, we have this problem. Section review question 9 said that if the concentration of HI is the requirement, said H2 and I2 each individually equals to 4.79 10 to the power minus 4, and K is equal to 54.3. How to calculate the concentration? Simply write the equation of the K, write the equation, the formula equation, balance it. We have balanced the equation, and then it will be H2 squared divided by I2 and H2 concentration. The denominator of K is 1, cross multiply both sides, you'll get what? K multiply H2 and I2 concentration equals HI squared. So in order to find, just take the root, square root for both sides, you'll get the HI concentration. So the square root of K multiply the concentration of H2 and I2 will be the concentration of HI. 54.3 is the K, 4.79 10 to the power minus 4 square. Why? Because these are both equal, and then the multiplication becomes the square of 1, and we will get the value of HI. So it's possible, the K is given, concentration of some reactant or product is given, asking to find the concentration of the other. And we have got the question 47 in chapter review, guys. Somehow tricky question, because there will be two K values, or we can say we call as the Q in order to be different than the K. The equation is given N2 plus O2 to form 2NO. Said K for this reaction is 0.01 at 2000 Celsius. The K is given. Okay. If 4 mole of N2, 0.1 mole of oxygen, 0.08 mole of NO are placed in 1 liter vessel at 2000 Celsius, predict which reaction would be favored. Which reaction would be favored, guys? In order to answer this question, we have to know this note, guys. The Q here, we can say this is K1 and this is K2 as well. The candle represents K1, K2, K1, K2, or Q. The K1 is the K which is given, 0.01. K2 is the K, the second K, which we, or Q, which we have to calculate through the given amounts and the volume, the concentrations. Okay, guys, for the same reaction. If, guys, if K1 is higher than K2 or Q, that means the forward direction is favored. If K1 is lower than K2 or Q, that means the reverse is the favored. If they are both equal, it means it's at equilibrium and neither side is favored. So how to first write the equilibrium for this reaction? Of course, the equation must be balanced, and then the expression is equal to Q, which is K2, we can say, NO square N2O2 to the power of 1. How did we get 0.08 for 0.1? From the given moles. Because the volume is 1 liter, so the mole is equal to the concentration directly. Or we got the what? The 0.016 as the K2. So in this case, guys, in this case, K1 equals 0.01. K2 or Q equals 0.016. Which one is higher? Of course, K2 is higher than K1. 0.016 is higher than 0.01. This is the case that the forward direction is favored. Sorry, the reverse direction is favored. Why? Because the K2 is higher than K1. K2 or Q is higher than K1. That's why we have to say that the reverse direction is favored in this mechanism. Notes about the K value when multiplied, divided, or reversed, guys. If a reaction reversed, K should be reversed as well. K should be reversed. Like what? In this, I have represents as equations. K reverse is equal to 1 over K forward. That's an equation you have to know. Like what? A said 2HI goes to form H2 plus I2. This is the reverse of the above. So if K is equal to 25, K reverse is equal to 1 over 25, which is K forward. This is K forward. The second equation, guys, if divided the reaction by any factor, the K nu equals Ko, the K given, to the power of 1 of the factor. For example, divided by 2, it will be 25 to the power of 1 of the factor, 1 of 2, 1 over 2. If it's divided by 5, it will be K odd to the power of 1 over 5, and so on. If it's multiplied, guys, K nu is equal to what? K odd to the power of the factor, to the power of the factor. Here in this reaction, guys, it's not, H2, I2 goes to form HI. But you can say, you can see that 1 over 2, 1 over 2. So it's divided by 2. Divided by 2. We can say it's the square root of K odd, or K new is equal to, the division is equal to K old, which is 25 to the power of 1 over 2, which is the same as square root of 25. And the last one, it's reverse it compared to the main equation, the first in the question. It's reverse it and divided by 2. So for the reverse it, we have to say 1 over K old. Okay. For this divided by 2, we have to say 1 over 25 over 1 over 2, or we can say 1 over square root of 25 is the same. If it is divided by 3, you have to say 1 over 25 or square cube of root of the 25, or 25 to the power of 1 over 3. 10 divided by 10, 1 over, reverse it and divided by 10, 1 over 25 to the power of 1 over 10. Multiplied by 5 and reverse it, 1 over 25 to the square of 5. That's how we can derive the new case in any case of the reactions. This is a standardized test, guys. As you can see here graphically, this is one of the graph that represents what? Represents the equilibrium position, but the line is, the forward and reverse are not on the same line. Let us solve the ministerial exam question, guys, in this section. This reaction in equilibrium, okay, concentration of H2I2 is given, HI is given, value of equilibrium constant of the reaction. So simply the K is equal to HI squared to the power of H2 and I2. Let's just put the values, you'll get the value of K. The following reaction that's at equilibrium state, and if concentration of each Cl2, PCl3, PCl5, which are the reactions and products, are given, 5 for the Cl2, 0.05 for PCl3, 2.5 for PCl5, respectively, the value of K. So just write the K equilibrium constant equal to PCl3 multiply Cl2 PCl5. Just put the numbers. PCl3 is 0.05 multiply Cl2, which is 5, divide by 2.5. You'll get the value of K. The reaction, this reaction is given, reaches to equilibrium when 5 liters of the vessel is given. This was the reaction, the problem which we have solved. The concentration of AB2C, the mole is given, mole of the B2 is given, mole of AC is given, the equilibrium constant equal what? The technique is that while the equilibrium expression, which is equal to B2 AC concentrations, AB2C, just calculate the concentrations by dividing the mole to the volume. Mole to the volume, you'll get the concentration and put the numbers there. You'll be able to calculate the K. Chemical reaction is at equilibrium when forward and reverse reactions are stopped. No. K is equal to 1, not always, because we have equilibrium K less than 1, K more than 1. Forward and reverse reaction rates are equal, yes. So C is the correct answer. No reactions remain. C is the correct answer. Why? Because in all of the cases of equilibrium, forward and reverse must be equal. That's the end. That's the end of the section. Thank you for the attention.